Okay, we're here with the second part of our lecture number 5, talking about defects in the crystal structure of metals. I mentioned last time when we were calculating theoretical density that the theoretical density is always higher than the experimental or empirical value. That's one reason why people that were dealing with materials began to consider and design material properties based on the fact that there are defects present. The other reason that we knew that the 3D crystalline structure of a metal wasn't perfect is that if it were perfect, we could calculate the number of bonds across any area. And if we knew the number of bonds and we knew the bond strength, then we could calculate the resistance to deformation across an area. And when you do that, you get a value, a theoretical value for strength that's 1,000 times bigger, sometimes 10,000 times bigger than the actual value. And so I just have on this slide some examples of a theoretical calculation for shear strength versus a experimental value. So we have 3 different kinds of defects. We've talked about vacancies as one of the types of point defects. We're going to start there with the other kind of point defects, talk briefly about the other 2 types of defects, line defects and surface defects. And then we'll come back to point defects and go in a bit more detail. So a process, you might know it as alloying, but officially it's solid solution strengthening. That's a way that we can strengthen metals by adding impurity atoms that diffuse into the metal itself. And there's 2 types of impurity atoms. One type are called the substitutional defects, and substitutional defects take the space of an absent host atom. And so in other words, they move into vacancy spaces. So substitutional impurities diffuse by moving into vacancies. So as there are vacancies in most metals, the impurity atoms can just jump into those spaces and then jump further into the surface of the metal, because diffusion will always happen from high concentration in the direction of lower concentration. So if the impurities diffuse by moving into vacancies, that defines the substitutional impurity. An interstitial impurity atom is one that will occupy a space between the atoms. Oops. So that's the difference between those 2 types of atoms. And because there's many, many spaces between the atoms and no need to wait for a vacancy, interstitial diffusion will happen faster than substitutional diffusion. The next type of defect is a line defect, a 2-dimensional defect, and these are called dislocations. Now, I'm going to draw a sketch here just to show you what a dislocation looks like in 3D space. So give me 1 second to do that. Okay, so this might be in 3D space an array of atoms, and I could see that I've got a plane here and a plane here. I think I want a different color. So if I look at this, these are just like stacked up planes of atoms. And so we can say that they're moving, they're all stacked up in a row. And all of them are the same except for one, and that's this one. This one sort of is wedged in between these three on the left and these three on the right. And this atom and every atom behind it going into the material is missing a bond. So it has a much higher energy because it's missing that bond. It does not like that state of being, and it's going to try and lower its energy by having bonds throughout. And then let's say we apply a shear stress like this. So as I apply that shear stress, at some point, I've got so many different colors going on here. At some point, this bond between these two atoms is going to break, and a bond will form here. And now, effectively, my dislocation is moved one atom or one diameter to the right. Now, this atom and all the ones behind it are missing an atom, are missing a bond. And now I have 4 full stacks and a dislocation and 2. And the dislocation, called the line defect, is the row of these atoms going into the board. That line is the dislocation. And with some more stress, and I'll have that bond broken and this bond formed, and now here's my dislocation. And then that will continue, and the bond will form here, and the dislocation will be at the top. And so I start out with a shape that's this big. And I end up with that increased dimension here, and effectively well, that sucks. Did I just lose it? Well, sorry about that. I end up with that. Here's my original length. And now I have this much increased length. And that is how, that is what what happens, how this is formed. Dislocations are formed when stresses causes planes of atoms to slip. And that's actually a science term, to slip past one another in slip directions. So dislocation motion is necessary for permanent deformation. So I have this defect, it's called a dislocation, and the dislocations strengthen through a process called strain hardening. Strain hardening increases the number of dislocations. Separate from that, or alongside that, is this truth here that deformation, permanent deformation, occurs when dislocations move. So if we want to strengthen a metal, all we have to do is prevent the dislocations from moving. All right. So I want to maybe start a flow chart here to talk about what these defects are doing. So in order for deformation to occur, dislocations have to move. In order to make a metal stronger, I need to prevent this permanent deformation. I do that by preventing the motion of dislocations. So we talked about substitutional and interstitial impurities. And what those are our point defects. And what they do is they create their presence in the material, causes them to create a stress field. And that stress field around the dislocations prevents them from moving. So it creates a stress field that acts as an obstacle to dislocation motion. And by doing that, I now have this obstacle to dislocation. I'm going to require more stress in order to get dislocations to move. I don't really want to start with causes. Obstacle to dislocations, which means more stress is then necessary to move dislocations. And that effectively means we've strengthened the metal. So that's what happens with the substitutional and interstitial impurities. They create a stress field that makes it harder for dislocations to move. We've just talked about the line defects, which are dislocations. The process of cold work or strain hardening increases the number of dislocations. The number of dislocations is increased by applying strain to the metal, which is cold work or strain hardening. And dislocations are obstacles to one another. Dislocations repel one another. And so more stress becomes necessary to move the dislocations past one another, which strengthens the metal. So this is a point defect. This is a line defect. And the last defect is called a surface defect. And a surface defect is known as a grain boundary. Or in other words, surface across which the crystal taken there. There we go. Is rotated to different orientation. So a dislocation might be moving in a crystal, but when it reaches the edge of that crystal, that boundary, it can't cross. So surface defects, just like the other kinds of defects, create an obstacle to dislocations, which makes it necessary to have more stress in order to get deformation. So here we are, grain boundaries and our surface defects. And we strengthen by this process called recrystallization, which increases the number of grain boundaries. Okay. So we've talked about the three kinds of defects: point defects, line defects, and surface defects. I want to go back now and do a little bit more in-depth discussion of point defects, and we'll get to the line and surface defects down the road. So back to talking about point defects. Specifically the impurity atoms type of point defects. We've got the substitutional impurities and the interstitial. And like I said, the substitutional impurities are those that take up the space left behind when a atom vacates a lattice position. So they diffuse because by jumping from one vacancy to another. If there aren't any vacancies, substitutional diffusion can't happen. So things like nickel might diffuse into copper. One metal diffusing into another. And it can't just be any metal. Not all metals can diffuse into one another. Some are actually can't be diffused at all, and some can be diffused 100%. There's three major rules that must be followed in order for an atom to be able to dissolve into a metal. First is that the difference in size, say radius or diameter, the difference is no more than 15%. If it's more than that, it just can't fit there. The second rule is that for one metal to diffuse into another metal, they should have the same crystal structure. So BCC can only dissolve into BCC. FCC, you might recall, is called the closest packed structure. And it diffuses into FCC, but it can also diffuse into a structure which we're not going to really look at too much, called the HCP structure, hexagonal close packed. It's also a close packed structure. So BCC only dissolves into BCC. FCC and HCP can dissolve into one another. Third rule is that their valence has to be the same. Now, many metals can have more than one valence, and that makes it easier for them to dissolve. So I will be handing this chart out. I put this together so we can look at the differences in crystal structure and valence and radius to see what would dissolve in iron. So that's what I've got highlighted here. So we see iron is BCC. So any metal that's not BCC can't diffuse into iron. So we can't do nickel, can't do cobalt, copper, zinc, platinum, tin, aluminum, silver, gold, titanium, or lead, according to them having to have the same crystal structure. So the next thing is to look at the radius. The radius of iron is 126 picometers. So magnesium, yeah, that's very close. And chromium, very close. A 15% difference would be like around 18 picometers difference. So those two would still be. Vanadium is close enough. Molybdenum, 139, that's 13, that'll work. So will tungsten, so far. And that's all we have for BCC. So for all the BCC metals, they all meet that rule about having a similar radius. So the last thing is to look at valence. And iron can be valence 2 or 3. So manganese, 2 it can be a valence of 2, so it would work. Chromium is 2, it would work. And vanadium is 2, 3, 4, or 5, it would work. Molybdenum, 2, 3, 4, 5, and 6, it's okay. Tungsten, only a valence of 6, so tungsten is out. So in iron, we can diffuse manganese and chromium and vanadium and molybdenum. That's diffusing in iron at room temperature, at standard pressure temperature, because at that temperature, iron is BCC. But at an elevated temperature, iron is FCC. So when iron is FCC, I'm going to go ahead and erase these marks. So when iron is elevated in temperature, it could be FCC. It becomes FCC. So then now it won't. It isn't soluble in BCC metals. So we eliminate a different group. All right, so, and it's FCC state. Copper, very similar, it's okay. Zinc, all right. 139 for platinum, that's okay. Tin, 140, that's okay, but it's getting close. 143 would be 17 picometers away. That's really on the edge, but maybe aluminum. But then I'm not sure that silver, gold, titanium, or lead would be able to diffuse based on radius. Okay, so then if we look here, copper can have a valence of 2. Zinc can have a valence of 2. Platinum and tin can have a valence of 2, but aluminum has a valence of 3, so it can't diffuse. So when it's when it's FCC iron, we could diffuse nickel and cobalt and copper and zinc and platinum and tin. Now, all we know is that there is some solubility for those. In some cases, it'll be a lot of solubility. In some cases, it won't be any at all. But you could use this method to determine which metals you can alloy into other metals. All right. So that's for substitutional impurities. For interstitial impurities, the atoms, whatever's being diffused in has to be small enough to fit into the spaces between the metal atoms. And the only things that can do that are carbon, oxygen, hydrogen. And carbon diffusing into iron, of course, that's what steel is, carbon and iron, plain carbon steel. All right. So one other slide here, just to illustrate how adding impurity atoms strengthens a metal. If the impurity atom is a little larger, then it's going to create a residual compressive stress there in the lattice, and that's going to be an obstacle for dislocations that are moving. If it's a little smaller, then there'll be a residual tensile stress. Again, it would slow down or prevent entirely dislocations and moving in that area. So if I've got 100% copper, that's at this side of the graph, copper would be the solvent, and nickel is the solute. And as I add nickel to copper, we can see that the tensile strength increases. And it continues to increase all the way up till 40% copper and 60% nickel. And then it starts to drop again as we have less and less copper until we have no copper and 100% nickel. So you can see that nickel is stronger than copper, but this combination, if I had 40% copper and 60% nickel, that combination is stronger than either of the two separately. And that's because of the presence of those substitutional impurities and the stress fields that they're causing. All right? That's it.